3 in a multiple regression with several other explanatory variables is less than 2, then what? So we're looking at estimated slope. So that's a B3 for variable x3. If the value of the t-statistic, where do these t-statistics come into play here? Well, remember that we have a little bit of an uncertainty about the slope, and we can come up with a confidence interval for the slope. And that tells us that we might have some error in the model or some uncertainty in the model, something wrong with the model, but mainly based on the idea that our sample is not truly representative of the true model. It's an estimate. And what if that confidence interval of the slope includes the value 0, such that for our model, it could be b0 plus 0 times x. If 0 for the slope was within this confidence interval, then it would tell us that that model is basically useless because it has no relationship. It doesn't show any relationship between y and x. Y is some constant value plus 0, not dependent on x. If that's the case, then our model is no good and we can toss it out. It's a hypothesis test that the slope in our regression model is not 0. Therefore, the null would be it's 0, is not 0. Therefore, the model does have some explanatory power. It is of some use. So how do we determine that? Well, we do the same thing we did in the first half of the class. We do a t-test. How many standard errors is the slope away from 0? So that's what we're talking about here. So we're going to do a t-stat, and we don't care whether the slope is positive or negative. If it's away in a positive direction or away in the negative direction from 0. So we're looking at a two-sided t-test. So if the t-test is less than 2, then what happens? So, in a standard t-test, if t is less than 2, it means that the probability of making an error is greater than 0.05, an error rejecting the null. So we can't really reject the null based on that distance. Okay. Does that say the slope is 0? No, it says the slope might be 0. In color A. We can't say it is 0. But it could be 0. And in fact, the smaller the absolute t value is, the more likely that the true slope beta 3 is 0. So again, we're swearing if we say the slope is 0. We should say the slope could be 0. How about B? The p-value of the t-statistic is less than 0.05. Well, remember, if the t-stat is less than 2, then the probability of incorrect, the probability, start to lose it tonight, probability is going to be greater than 0.05, right? If the t-stat is 2, you're 2 standard errors away from the null. It means the probability of rejecting the null erroneously, type 1 error is 0.05 or 5%. If t is less than that, then the probability is going to be higher. So it should be greater than. Oops, don't want to do that. Not less. So that's wrong. How about the R squared of the fitted model is larger than 5%? Well, R squared is a measure of how well the model explains Y, or of what portion of variability is explained by the model. So the t-stat doesn't have anything to do with that. The t-stat in particular of only one variable is not telling you anything at all about um, how much of the variability in Y is actually explained by that part of by the model as a whole. That's what the R squared tells us. So that's completely wrong, unrelated. How about D? D says the 99.7% confidence interval for B3 contains 0. Well, most people are going to read this through in a time critical test, and they're going to say 99.7. That's not 2 standard errors. That's 3 standard errors. So that can't be right. But remember, if the t-stat, the count of standard errors, is less than 2, that means somebody's talking here. Let's see who that is. We'll turn you off. Sorry. That means that the 95% confidence interval contains 0. So a plus or minus 3 standard error confidence interval is wider and also contains 0. So if we're looking at a 95% confidence interval, we're looking at a t count of 2, and so that means that the 95% confidence interval is this wide, plus or minus 2 standard errors. Our 99% confidence interval must be based on 3 standard errors, so it's even wider. So if the 2 standard error interval contains 0, then obviously the bigger interval also contains 0. So that is the correct answer. So we have to explain one more incorrect answer. There cannot be a statistically significant marginal correlation between X3 and Y. What's a statistically significant marginal correlation? Don't confuse this marginal correlation. That's not a linear relationship. I'm not sure what it is. I'm not sure I understand the words, but when we're doing a t-test, we're trying to figure out if there's a I can't even say statistically. I can say heteroscedasticity, but I can't say statistically. A t-test is trying to find out if there is a statistically significant linear relationship between X and Y. Okay, so the correct answer for that one is D. Any questions? If not, we'll go on to question 7. R squared in a multiple regression. Remember, R squared is what portion of the variability in Y is explained by this model. And one thing that we learn, we memorize, is that when you add another variable to the model, you don't detract from the value of the existing variables in the model. So it can never go down as you add a new variable. So if we have our age versus height model and we add some new factors into it, they can't detract from the value of using age as a predictor for the height of a kid. So R squared can never go down. We can't make the model worse by adding variables. We might not be making it any better, but we can't remove value from the initial existing variables. So A, yes. Additional variables. Can't reduce the explanatory power of the previous variables. Therefore, R squared can only go up. Okay, let's look at the others answers which are wrong. R squared in a multiple regression always moves in the opposite direction to RMSE. A little bit tricky. Remember, R squared equals 1 minus RMSE squared over standard deviation of Y, or the variance of Y, standard deviation of Y squared, or the variance of Y. But a key thing to remember is that RMSE does not have to decrease when we add a variable. And I'll refer you to see notes from class 7. Slide 15. Don't take my word for it. Take Professor Waterman's word for it. How about C? R squared increases whenever a leveraged outlier is removed from the data. A leveraged outlier, we talked about this a little bit earlier, right? It's one that's kind of far out. Would R squared increase when we remove that from the data? No, it actually can go the other way around, right? A leveraged outlier has strong control. And so even if it's right on that regression line, it helps to anchor that regression line. And therefore, the fact that it's further out and you've got an anchor point that's farther out, it means that the model is likely to have better explainability. I think that's a word. So R squared would tend to go down if you took out that good leveraged data point. How about D? R squared, does it increase whenever an insignificant predictor is removed from the fitted model? What's an insignificant predictor? Well, an insignificant predictor is one that could be zero. So this would imply that R squared goes down with more variables. Implies. So in other words, if we took a model that we have with a certain R squared and we added in a new predictor, explanatory variable, we know that R squared could be the same or could go up. Now, if that predictor is insignificant, and that is, in other words, we can't say that it's not zero. We can't reject the idea that it might be zero. It would mean that if we removed it, then and R squared increased, it means that when we put it in, R squared must have gone down in the first place. And we know that can't happen. You can't put, especially an insignificant predictor X variable in there and have it remove the explanatory power of the other variables. You can't reduce them. Make sense? Okay, how about E? R squared in the multiple regression, is it always larger than the RMSE of the fitted model? No, of course not. R squared, kind of like correlation, is scaled to 0 to 1, somewhere between 0 and 1. Remember, it's divided by, the RMSE is divided by standard deviation of y, or if you look at the original value, it's the sum of the squares of the regression divided by the sum of the squares of the total of the data. So it's scaled such that it can be no larger than the total. But on the other hand, RMSE is not, and I hesitate to use the term normalized, but mathematically that's what it would be, is not scaled to 0 to 1. It's still in the original units. So if our units are millions of light years, then RMSE would be measured in millions of light years, and it could be in any number. Okay, so E is not correct. Okay, moving right along. We've got a few more to go yet. How about number 9? This is a little tricky. We really haven't covered this so much, but it's one to remember. In order to capture a situation in which one expects to find for small x that y is increasing in x, but for large x that y is decreasing in x, then a natural formulation of the model is to do what? Well, let's take a look at what the question is saying. If this is our model, or this is x and y, if for small x, that is small values of x, and large x would be further to the right, if for small values of x, y is increasing, and for large values of x, y is decreasing, then we don't have a linear model. We can't use a linear model to describe that kind of reversing relationship. So we can't do this. not a linear relationship. But we could do a transform of some sort. We could transform the data, build a linear model from the transformed data, and then, if necessary, untransform the y values or the results of the model. And we might be able to do something like this. So instead of regressing y on x, what if we regress y on the log of x? So a transformed x transform. Well, the problem is a log, it's constantly increasing with x. It doesn't go down. So a log only increases. So we can't do that. That's not going to work. How about regress log y on x? Same idea, except of course it's the other, kind of the inverse. So that's no good. Regress log on 1 over x. Same idea. It's 1 over x does not reverse. How about E? How about a second order polynomial? Well, a second order polynomial looks like this or this. So for example, y is a function of x squared would be a second order relationship. And if we wanted to undo that, we would regress against a second order polynomial of some sort. So that would be, if we want to correct that curvature, that second order curvature, we would regress against a second order polynomial, converting it into a linear relationship. Everybody get that? We didn't talk about that earlier, but that's something you've already covered, I believe. Though maybe not in great detail yet, but enough in order to be able to answer that question. No questions. Okay. Now we get to some of the more complex ones. Here we go. A company makes cash advances to small businesses, makes loans. One of the outcome metrics that the company uses to judge the quality of an advance is the performance of the advance after the first 3 months. So you make the loan, 3 months later, you go back and check on what's happening. The performance is defined as the ratio of the actual amount paid back to the expected amount paid back. How much do they owe at the end of 3 months? How much did they actually pay? The company is interested in identifying predictors of 3-month performance and has started off by looking at the age of the company in years. So this would be X. To this end, they ran a simple regression of performance against years in business, and the output is below. Okay, so let's take a look. What do we got? We have a nice picture. We have a bunch of data points. Would you be willing to say that's an example of non-constant variance? We got a big cluster down at X, and we have just a bunch of little dots, and it looks kind of like it goes that way, but be very careful. The fact that we have fewer data points and a sparse collection of stuff in the higher X value, larger number of years in business, doesn't mean that our variance is not constant. You realize, of course, that in a normal distribution, the probability of getting numbers much further out is fairly low. So if you don't have a lot of numbers to start with, the probability of actually having a value that lies way out in the tails is lower. So be careful of seeing a low density of tail points in a low density region of your data. That doesn't necessarily mean you've got non-constant variance or the spread of the data changes. It's just a consequence of the probability of data being in the tails is much smaller. So there are tests, some tests that you can look at. We'll talk about those another time. Anyway, so we have some summary stuff here. We have summary of fit. We have R squared. We have an adjusted R square. We haven't talked about that. We'll talk about that again in the future. It's an adjustment that's done based on residual degrees of freedom. We're always going to reduce R squared to something that is maybe a little bit more accurate when you've got, especially with a multiple regression model. We have root mean square error. That's RMSE, right? That's a measure of the variance of Y above and below the regression line. The mean of response, remember what that is. That's Y bar. That's the average of everything. Not the average of the distance of Y from the regression line. It's just the average of all the Y values. Observations, that's the sample size. Okay, how much data do we have? Parameter estimates, what do we have here? The intercept and years in business. Well, intercept is the B0, and years in business is the slope in a regression model. So what we're saying is that the performance ratio equals B0 plus B1 times the number of years in business. That's our model. And so it's going to equal, in this case, 0.86 8637, and I'll round it up to 6, plus 0.002 times years. That's what the model is. That's what that table is telling us. Okay. So what do we have here? We've got a model. We have a positive slope. The red line shows you what the regression model line is. You can see we've got a lot of variation above and below it. We have a measure of that called RMSE, which is 0.39. Again, that's not scaled to 0 and 1. It's dependent. It's the same units as the Y value itself. Let's answer some questions about it. The equation of the fitted model, which we just talked about, implies that what? And don't forget, let me just put a note here. Higher performance, the performance measure is better. Let's just remember that. So the equation of the model implies what? That years in business has no association with advanced performance. That's not correct. What do we have here? We have a T ratio, 2.94. That's pretty good. T equals 2.94. P is very small. And that tells me that the true slope is not likely to be 0. We've done a t-test on the slope. We see that the confidence interval of the slope does not include 0, so we reject 0, reject the null. So there is an association. There is some kind of relationship. Question, what different graphs of functions do we need to know? Log, second order, polynomials, others. It's handy to know log, exponential, second, maybe third order polynomial. That's probably about it. We'll talk more about that in a future tutorial session. We'll talk about Tukey's model and a ranking of transforms to use either on the x variables or the y variables. We'll go into that in much greater detail in a future session. Okay, how about B? Does the model say or imply that older companies on average have better performance? Well, remember the model says performance is equal to something, some constant, plus the slope times the age. And we have a positive slope. It's plus 0.00204449. So more age implies higher number or higher performance. So that is the correct answer here. Let's go back and look at the rest of them, see why they're wrong. Younger companies on average have better performance. No, this is the opposite of B, the correct answer. This would mean that you would have a negative slope, negative B1, which is not the case. So that's not correct. How about the average performance of startups is 0.8814. What's a startup? It's a startup. It's a company that has a small age or low number of years in business. And if we look back at the table, where did that 8814 come from? That 8814 came from here. It's the y bar of all of the y values. So the average of all companies is 0.8814, not just startups, not just new companies. So that one's not correct. How about E? The equation implies that the years in business has a small and statistically insignificant effect on performance. Is it a small effect? Yes. We see that B1 is equal to 0.002 approximately. That says if we double the number of years of the company, we only increase the performance by 0.002 more. So that's a small effect. R squared, 0.0025. So it says that the years in business only explains about 0.25% of the variation in performance. That's pretty small. But is it statistically significant? And I say insignificant. The answer there is no. T equals 2.94. So even though it's a small effect, It is statistically significant. So that answer is also incorrect. Okay. All make sense? Okay, we'll move on. The fitted model implies that a 10-year-old company would have a performance ratio of about what? Well, this one's easy. All we need to do is calculate what the model tells us. So Y, the performance measure of a company, equals, and remember we put the model together, 0.863, make sure I copy this down right, 7598 plus 0.0020449 times x. Well, this is the intercept. Some constant plus the slope times years in business. Or y equals b0 plus b1 times x. So let's go ahead and plug in 10 for x, and we calculate y to be 0.8842088. So 0.864 plus 0.002 times 10 is 0.884. Not a big change, but that's what the performance ratio comes out to be. So that answer is right here. And we can just directly pick the correct answer, A. I like those where you can calculate the correct answer. You don't have to puzzle about the wording. Is that really what it says it is? Does that disqualify that answer the way it's, give me a number. I'm an engineer. Suppose that the company uses this model to predict the performance of a small business that is 5 years old and is not in this sample. If we accept the assumptions of the simple regression model, then the fitted model can predict the performance of this business with 90% probability to within plus or minus what? So remember what we're trying to do here. We're using a prediction. We're trying to predict a new value, and so we're talking about a prediction interval. So what are we looking for? Now, we need a prediction interval of what? We need a 90% prediction interval and so that is basically plus or minus 1.645 standard deviations. But what's the standard deviation of the variability above and below the model? That's the RMSE. So we can go ahead and calculate RMSE is 0.390547, which is an estimate of the standard deviation of the errors. So plus or minus 1.645 RMSE equals a range of 0.642450. I think that's right. Double check my calculations if you would. And lo and behold, that number is up here. So B is the correct answer. What are these others? What, typically you can expect the wrong answers to be some kind of confusers. They're based on something that looks like a real number, but it isn't. 0.78104, that is plus or minus 2 RMSE. And that's not good. That's not correct because that would be a 95% prediction interval. How about C? What's 0.3904? That's 1 RMSE. We know that's not right. That would be, what, a 68%? What's 0.881482? Well, that's the mean in the table. And what's 0.002045? Well, that's the slope coefficient, B1. So that's not the right answer. Another one, easy to get. If you know how to calculate what a prediction interval is. And if you forget, we go back to this picture, plus or minus some number of RMSE. RMSE is a measure of the standard deviation of the errors in Y around the regression line. The residuals, I should say. Okay. Had the performance ratio been expressed as a percentage, meaning that it was simply multiplied through by 100, then which of the following equations would describe the regression line on this new scale? X has not been transformed. So what this is it's just a linear scaling. So all we need to do is multiply all the coefficients by the same factor. So instead of y is 0.86 plus 0.00204 times the years, now it becomes 86.37 plus 0.204 times years. And do we find that up here? Yes, we do. We find it in B. So again, all we need to do is calculate the correct number. How about A? A was the original model, right? I think so. Yeah. This is the original model. So that's going to be off by a factor of 100. C is the model divided by 100. That's the wrong way. Well, I should be using red here. Huh? D, all the logs. When we're just expressing the output as a percentage, we're not talking about elasticity here. We're not talking about percentage change in X and a percentage change in Y. We're just multiplying by a constant. So any log transform, any log relationship is incorrect here. Okay, how about a consultant had earlier stated that an additional 5 years of age on a small business would equate to an expected improvement in performance ratio of approximately 0.02. So 5 years. If we accept the assumptions of the simple regression model, then, and so they put that in there to make sure you didn't argue about the model not being good because of heteroscedasticity or independence or something like that. The model's good, but he said the consultant had earlier stated, before we did the model, he said he thinks that if you add 5 years, you would improve the performance ratio by 0.02. Is that correct or not? So the consultant says, add 5 years and therefore the performance increases by plus 0.02. So if, but now based on our model, where the slope B1 is 0.0020449, that means that the change in y for a change in x is 0.002 roughly. And so if delta x, the change in years, is 5, then the change in performance, delta y, is equal to 5 times 0.002, or approximately, which is equal to 0.01022245. Okay, well, that's not the same as the consultant's prediction, but it says, the model says it's a smaller improvement for 5 years than the consultant says. So B is possible, too optimistic. So B is possible, it's a possible answer because it is smaller. That is better performance. But is our model, is that slope is it significantly different than what he predicts? So what about the confidence interval of the slope? So is it supported or not supported by the model? So let's look at the confidence interval. So the slope is 0.002 plus a bit, plus or minus 2 standard errors. Remember that we normally will use a 95% confidence interval for anything, even if the other questions specify a 90%. That's not what we're working with. So that's plus or minus 0.00696. So the slope could be as high as 0.0034369. That's 0.002 and change plus 2 times 0.0006 or 0.001, basically 135. So 5 times this, three, four, roughly, is 0.017. Can't read my handwriting here. Something 845. Is that right? Which is still smaller than the consultant's prediction. So what we're really doing here is we're kind of doing our own version of a t-test where our null hypothesis is based on a slope that turns out to be more than 2 standard errors of the slope away from what our model says. So we would say in that case that the consultant's claim does contradict. So A is wrong. How about B? The consultant's claim is too optimistic and is not supported by the model. The model says the slope is wrong. I mean, his slope is wrong, and it's wrong by being too large. It predicts too high a performance, so it's too optimistic. So that is, according to our calculations, the correct answer. And of course, the opposite answer of that, too pessimistic, that would be a slope. For his slope would be smaller. That's not the correct answer. There's no output to present this claim. Of course not. We have info on slope and confidence interval of the slope. And how about RMSE is too large to adequately to address the claim of the consultant? Well, no. We're actually using RMSE to calculate standard error and all that sort of stuff, and so it's actually a good number to allow us to make this conclusion. Any questions on that? Okay, next one. Here's a residual plot. A plot of the residuals, that is the errors that are left over above and below the regression line. So it's not only the errors that in the true model that are due to other influences, other factors that might influence the outcome y, but also errors due to our sample being not quite a perfect estimate of the true model. And so we're plotting all of those residuals, the measures above and below the regression line of the y values. And we can see we've got a few things going on here in the tail areas. And so what does that tell me? It tells me that because it's lower, because it's lower slope at the edges there, it says that this is denser data, and then it says that the tails don't go out quite so far. Less dense. And so what that tells me is that it is light-tailed. A little tricky, right? But you've got that set of samples on your earlier cheat sheet, and you remember about the slope, meaning that the data in that region is a little denser. And of course, the trick here is that if it's denser a little bit further in or a little bit closer to the center, then it means it has to be less dense the further out you get. Therefore, the tails themselves, the outer part, is lighter. That is, it has less data going out that far. Okay, so that's some information we have about the residuals. Based on the above graphic for the residuals from this model, what do you conclude? So we know from this the residuals are light-tailed. And what do we see here? Well, A, it says the residuals are heavy-tailed. Well, no, we know that's not true. B said just what we concluded, that the residuals are light-tailed. That is the correct answer. How about the residuals lack independence? Well, we can't tell from a normal quantile plot of the residuals. We don't know. Are they independent or dependent? Don't know. How about the residuals lack constant variance? Well, we don't have a scatter plot here. If we had a scatter plot, we could see whether the 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 cloud of data points spreads further out or becomes less spread out. We don't have that information. The residuals may be bimodal. Well, the histogram here says no. Histogram is not bimodal. So that one's wrong, and these ones we don't have enough data here. Can't tell from this plot. So those are both wrong. Make sense? How about the business with the largest positive residual is the Treasure Casino. The fitted value of this model for the Treasure Casino does what? Did we have a scatter plot here? Yeah, we did. So the largest positive residual, kind of hard to tell. We have so many dots here, it's hard to tell which one's the largest, but one of those is way up in the positive direction, so it's bigger than the regression line. So something way up, something up here in that region. So what do we find out here? So if the positive residual is big, then the fitted value of this model, that is the predictive one, the spot on the line that should correspond to the Treasure Casino is much smaller than the actual one, is lower. So the predicted on the line value is less than actual by a lot. So by knowing that, we can actually say A is the correct answer, right? It predicts a performance for the casino that is unusually smaller than the actual performance. What is unusual? Unusual means it's more than most of them. It's a English term, not a technical term, so it's approximate, you know. How about B? Ooh. Stop that. B, predicts a performance for the casino that is unusually larger. No, the prediction Treasure Casino, this is the predicted, this is actual. So the actual is much larger. The prediction is smaller. So B is wrong, just the opposite of the correct answer. How about predicts a performance for the casino that is smaller than the actual performance by a typical amount? No, it's the largest. And I say largest is not typical. How about predicts a performance for the casino that is larger than the actual performance by a typical amount? Well, it's not larger and it's not typical, so that's wrong. How about E? Is unreliable because this observation must be corrupted. Must be. Now, you've heard about, getting rid of outliers that might not be good data. They might be corrupted data. But you've got to look into it very carefully. This may be the largest residual, the one that's furthest away from the predicted value, but that doesn't mean that it has to be corrupted, that the data itself has to be bad. Casino maybe pays back its bills much better than other kinds of companies. So that's wrong. uh, so I'll just put some notes down here, maybe. A positive residual means that the actual data is larger than the model predicts. And the largest residual is the farthest away from the model line. And A, the answer A, says the model predicts lower performance by the most amount. And I'd say most was unusual. Okay. Okay, last one. Taking the assumptions of the SRM simple regression model is true. You remember those. You've memorized them, right? Linear relationship, observations are independent, equal variance, and normally distributed around the regression line. If that's true, if this data has been augmented by an equal number of companies randomly drawn from the same population, what does that mean? It means we are doubled n, size of the sample. What happens? Does R2 increase? Well, you doubled the number of samples. Does that mean your model now becomes better at predicting? It might be, does it have more predictive power? It might be a little bit more accurate, but it doesn't have more power. So A, no. And you can remember, or you can demonstrate that by knowing that R squared is 1 minus SSE over SST. And these are likely to move together. And the other thing that to remember is that more data does not reduce sigma, reduces standard error, but not the sigma, the standard deviation of y. And so standard error over n and standard some of the squared errors over n and some of the squared total over n would stay the same. Okay, so A is not correct. How about B? RMSE must decrease. No. Remember, RMSE is the square root of the sum of the squared errors divided by n minus p. Well, sum of the squared errors now has 2 times the values, 2 times the terms. So we've doubled that. But n is also 2x. So 2x over 2x equals 1, no change. And we're talking about a large number. We have almost 4,000 observations, and we're going to add another 4,000 to make it almost 8,000, so that little minus 2, not relevant. How about C? The standard error for the slope estimate would increase. Well, that's also not true. Why? Standard error of B1, the slope, is going to be RMSE divided by the square root of n times 1 over the standard deviation of x. This is approximately the same. Remember, you've added more observations from a given distribution. That doesn't change the standard deviation of the data itself. The sample size n is larger. RMSE, as we've seen, is basically unchanged. So n is larger. The only thing that changes, and therefore the standard error is smaller. What does the answer say? Increase. So that's wrong. Just the opposite. How about the width of the confidence interval for the slope would narrow? Well, standard error is smaller. Confidence interval must therefore get smaller. Leads to a narrower confidence interval. Confidence interval is plus or minus confidence interval of the slope is plus or minus 2 standard errors. Two smaller standard errors means you have a narrower confidence interval. And finally, E, all of the above. Well, no, it's only one of them. That one. Okay. We've gone through all of the ones that I think we've covered up so far in the topics we've discussed tonight. Any questions on any of this? Anybody still hanging in there? Yeah, we have a few people left. So we did some basic stuff. Venkat, we talked about that much earlier, right? I'm not sure if you were here for that. Highly leveraged data point. Remember what a lever looks like, right? The longer the lever, the more leverage you have at the other end. If you change this end, you have more strength, more power on this end. So if you've got a regression line that looks like that, an X value in the middle doesn't have a lot of leverage. You move that up, yeah, it moves things up a little bit. You move it down, you move things a little bit. It doesn't change much on the slope. A point out here is leveraged. If that point is down there, it has a lot of pulling power, right? So that's a highly leveraged data point. It doesn't necessarily mean it's influential, because if that point was already on the line, it would just confirm the regression line that you have. But it has a lot of leverage. It could, if it were off of that regression line, it would have a large influence on pulling that regression line. Any other questions? And we can go into we'll go into more detail on that, I think, in the next stat session. Okay, if that's it, then I'll say good evening to everyone, and we'll see you again on Friday.